Hello, today we're looking at electrical resistance, reactance and impedance. This video follows on from the video on alternating current, AC, which I did in the A-level physics revision series. This video is itself not part of the A-level revision series because, as far as I know, there is no A-level subject which covers impedance. But please tell me if I'm wrong and I will put it in the A-level playlist. But as far as I'm aware, this material is more appropriate for students at university. So although we'll be looking at the AC effects, the alternating current effects on impedance, let's first just remind ourselves what we mean by direct current and the resistance associated with direct current. Direct current, for example, comes from a battery, and if you were to put a voltmeter across a battery and measure the voltage, this is the voltage, over a period of time, you would expect that as long as the battery has a useful life, that the voltage would remain the same unchanged. If it's a 9-volt battery, then the voltage will be a direct 9 volts, no change. If you then put that battery, here's the battery, across a resistance, R, then a current will flow. That current is determined, this battery has voltage V. That current and the voltage are related by Ohm's law, V equals IR. And so if the voltage is constant, and of course the resistance is constant, then that means the current is constant. So if you were to measure the current with, say, an ammeter, what you would find is this is the current, this is time. As you measured the current going through this circuit, for the useful life of the battery, the current also will be constant. And so you've got in DC a constant voltage, a constant current going through a constant resistance. Now let's take this circuit here and take the battery out and instead replace it by an alternating current supply. So we have our alternating current supply going through our resistance R. And the supply will have a voltage and there will be a current flowing through the circuit. And Ohm's law will still apply. V equals IR. But what you have to remember is that when you've got an alternating current, as we saw in the video that I've made on alternating current, the voltage is constantly changing. The resistance, of course, remains the same. So if the voltage is constantly changing, the current is constantly changing. And the mathematical representation of that is that V equals V naught sine omega t. That's V at any time t. And the current at any time t is equal to I naught sine omega t. So if we plot these on a graph, first we'll plot the voltage. That will have a sine wave shape. So at the voltage at any time, the maximum is V0. That's where this comes from. A sine term always goes between +1 and -1. So if you multiply that by V0, it means that the total voltage will vary between plus V0 and minus V0 in a sine wave. And the current will look like something like this. That's the current. Obviously the size of the current, the maximum of the current, will be determined by the size of the resistance. And you can also say that V at any particular time t is equal to I at any particular time t times R. So anywhere you choose, if we choose a time, say there, this is time of course, then V at time t is equal to I at time t times the resistance. And you'll notice that the voltage and the current are what is called in phase. That is to say, when the voltage is at its maximum, the current is at its maximum. When the voltage is 0, the current is 0. when the voltage is at its negative maximum, the current is at its negative maximum. It's in phase. And I want to introduce you to a concept called a phasor diagram. A phasor diagram purports to draw the resistance and the phase angle. So if I draw a little one up here just to show you, if I were to draw something like that, then the length of the vector, as it were, this length would represent the magnitude of the resistance, and this angle here, phi, would represent the extent to which the current was displaced from the voltage. In other words, instead of the current being exactly in phase, the current might actually start here and go up like this. As it happens, that doesn't happen with resistance. So the phase angle is zero. There is no difference in phase between the current and the voltage. So on our phasor diagram, you would simply draw the resistance like this. The length of the line is equal to the value of the resistance, and the angle, which is zero, tells you that the current and the voltage are completely in phase. Now the reason I do that, and that means that the so-called phase angle is zero. There is no difference between where the voltage is and where the current is. The reason I do that is because we're now going to discover two electrical devices where that is not the case. These two devices are capacitors and inductors. Let's first think about a capacitor. A capacitor is really just two metal plates opposite one another with a small gap between them. And if we think of it firstly in DC terms, so we're going to put it across a battery, then what happens? The important thing is that although a current flows, at least initially, no current ever flows, ever flows between the two plates. Never assume a current flows. Indeed, if there is a spark that jumps across, then it messes up the capacitor. The whole point of a capacitor is that no current flows between the two plates. That's crucially important. And indeed, for a proper capacitor, there's usually a piece of insulating material between the two to make sure that no current can flow. So what happens? Well, as it were, the conventional current flows from plus to minus. But what is actually what is actually happening in electricity is that electrons are flowing, and they flow from minus to plus. So the electrons will flow until they get to this plate, and then they will congregate on the plate because they cannot jump across the gap. That's the crucial point. And if you get a congregation of electrons, negatively charged electrons on this plate, those electrons will repel the electrons on this plate and push them. The electrons will now flow in this direction back to the positive terminal, leaving a residue of positively charged particles on this plate. In other words, energy has been stored. You could, if you wanted to, disconnect this capacitor, which is now fully charged, so it's negative on one side, positive on the other, and if you were to connect that to, say, a bulb, a flash bulb, then the capacitor will discharge through the flash bulb and it will flash. And that's the principle on which many flashlights in cameras work. You initially charge a capacitor with the battery in the camera, and then when you flash the flashlight, the capacitor suddenly discharges through the bulb, producing a very high intensity but short-lived light. And what we say is that the capacitance of this capacitor is equal to the charge it is capable of storing on one of its plates divided by the voltage. So you can see that as the voltage increases, so the charge that the capacitor is capable of storing will also increase. Now let's think about the other device, the inductor. An inductor is basically just a coil of wire, sometimes called a solenoid. So the current, if we connect this now to a DC device, the current will flow through the coil. But what do we know about a current flowing through a wire? Here's just an ordinary wire, and it has a current I flowing through it. We know that a wire that's got a current flowing through it will generate a magnetic field. That magnetic field will be around the wire. So if you think about the coil, at the top of the coil you've got a whole load of wires. Let's say the current is going in to the paper, and at the bottom of the coil you've got a whole load of wires coming out of the paper. So what we're doing is we're looking at the inductor and seeing the coil go round. So at the top the coil goes in, at the bottom the coil comes out, and the current is going in the direction of my pen. So when the current goes in, it will create a magnetic field around each of the wires in a clockwise direction. And when it comes out, it will create a magnetic field in the anti-clockwise direction. So you'll notice that inside the solenoid at the top, the field is travelling in that direction because it's going around like this. So when it gets to the bottom, the field is travelling in this direction. At the top, the field is also travelling because at the top, the magnetic field goes round clockwise. At the bottom, the magnetic field goes round anti-clockwise, which means that at the top of it, the field is going in this direction. Consequently, within the centre of the solenoid, you've got a magnetic field going from one side to the other. So that could be north that side and south that side. You create a magnetic field within the solenoid. And the flux associated with that field, phi, is L, the size of the inductance, times the current flowing through the wire. L is the measure of a conductor, of an inductor, and is measured in henries. C is the measure of a capacitor and is measured in farads. Now let's go back to our capacitor, and this time we're going to put it in a circuit which has an alternating current source. So there's the capacitor. It's exactly the same diagram as here, except that instead of a battery, we now have an AC supply. And the current, of course, because it's an AC supply, is going to constantly change direction. So electrons are going to form on this plate, then they're going to form on this plate, then this plate, then this plate, constantly changing. And the question is there a V equals IR equivalent for the capacitor? And the answer is yes, there is. What you find is that V is proportional to I, the voltage, is proportional to the current flowing through the wire, and the, as it were, the resistive effect, which we actually call the reactance, is given by XC. And by experiment it is found that XC is equal to 1 divided by omega C, where omega equals 2 pi F. And F is the frequency of the alternating current, the number of cycles per second. And C is just the capacitance of the capacitor. So you find that there's a resistive effect, which we call the reactance, which is equal to 1 divided by omega C. And what that means, of course, is that as the frequency increases, remember omega is 2 pi times the frequency, as the frequency increases, the reactance will decrease. So as the frequency goes up, the reactance will go down. So unlike a resistor, which doesn't care what the frequency of the AC is, when it comes to a capacitor, the actual resistive effect of the capacitor depends on the frequency of the alternating current. Now, why should that be? Why should that be? Well, let's think about it. What's happening is that the electrons are flowing onto the plate. And they are going to have the effect of repelling electrons from this plate, leaving it net positively charged. But of course they also do something else. Not only do they repel the electrons from this plate, but they also impede any further electrons that are coming in this direction wanting to join them on the plate. As the charge builds up, then like charges repel. Consequently, the charges that are already on this plate will repel the charges that are trying to come and join them on the plate, and ultimately they will stop the charges from flowing altogether. But it takes a bit of time for that to happen. So what is happening is, as the charge builds up on the plate, so the impedance of further charge being added to that plate grows with time. But of course, it doesn't get much time to do this, because then the phase of the alternating current changes, and now the electrons are moving in this direction. So everything changes sign. There are now electrons on this plate. There is a net positive charge on this plate, and the electrons coming in this direction are impeded. And the longer the time is, the greater will be the impedance. And now you can see why the resistive effect falls as the frequency increases. Because as the frequency increases, the amount of time that you've got for electrons to build up on the plate before the electrons start going the other way is reduced. Higher frequency means less time for each cycle. So consequently, you've got no time, or very little time, for the electrons to build up on this plate and then begin to impede the flow of electrons before the electrons are now coming the other way. So the higher the frequency, the less impact there will be, because there will be fewer electrons building up, and therefore a lesser effect of repelling the electrons that are still coming along. Whereas if the frequency is so long that, for example, there are several seconds before the current changes, then the electrons will fully build up on this plate, to the extent that it is even possible that they will impede completely any flow or any further flow of electrons, and so the current will completely stop. So the higher the frequency, basically the less time there is for electrons to build up on this plate and impede the other electrons that would like to try and join them before the current changes direction. But there is something else that is noted by experiment, and that is that if you plot the voltage across the capacitor, and remember it's an alternating voltage, so it's going to have a sine wave effect, V equals V naught sine omega t, and then you measure the current which is flowing in the circuit, you find that the current, let's put some points there so I can see what I'm doing, the current looks something like this. It is no longer in phase with the voltage. In fact, the current starts first and then the voltage comes second. So the voltage lags behind the current. This is the voltage, this is the current, and the voltage is lagging behind. The current does this, the voltage starts, as it were, later. And in fact, the angle is 1/4 of a full wavelength. And since a full wavelength is 2 pi radians, 1/4 of that will be pi over 2. So in fact, the voltage is minus pi over 2 behind, as it were, the current. It's 1/4 of a wavelength behind the current. And what you can also see from this is therefore that the voltage at time t most emphatically is not equal to the current at time t times the reactance. That is no longer true, because when the voltage is at its maximum, the current is 0. And when the current is at its maximum, the voltage is 0. So this certainly, voltage no longer equals the current times the reactance for any given time. What we can also do is to plot our phasor diagram. You remember the phasor diagram for resistance? For resistance, we plotted the resistance along here because the angle was 0. In other words, there was no phase angle between the voltage and the current. They were completely in phase. But now the phase angle is minus pi over 2, which is of course minus 90 degrees. So if we're plotting the reactance, the size of the reactance Sxc is plotted as the length of that line, and the angle is 90 degrees. In fact, it's minus 90 degrees, which is why I've plotted it downwards. So our phasor diagram for capacitors shows the modulus, if you like, the size of the reactance, the resistive effect of the capacitor, is represented by the length of the line, and the phase angle is represented as minus 90 degrees, minus pi over 2 on the phasor diagram. Incidentally, although this formula is not true because you cannot take the voltage at a particular time, what will be true is that the root mean square of the voltage, which we dealt with in the earlier AC video, is equal to the root mean square of the current times XC. So in other words, what we're saying is, taken over the entire cycle of the sine wave, the voltage root mean square is equal to the current root mean square times the reactance caused by the capacitance. Now let's take the inductor and put that into an AC circuit. So here's the coil or solenoid, and here's the AC supply. And what we want to know again is there an Ohm's law type of effect? Is there a V equals IR kind of equivalence as far as this is concerned? And by experiment you find that yes, there is. V is equal to I times what's called the reactance, the resistive effect of the inductor, but the reactance XL. And on this occasion, XL is equal to omega times L, where once again omega is 2 pi times the frequency. So whereas the reactance of a capacitor was 1 over omega C, for an inductor the reactance is omega L. And what that means is that, of course, as omega increases, in other words, as the frequency increases, the reactance will increase. So XL will increase as the frequency increases. With the capacitor, remember, it was the other way round. As the frequency increased, the reactance decreased. But here with the inductance, if the frequency increases, so does the reactance. Now, why should that be? Well, let's just think for a moment what's happening. I showed you earlier that the flux generated in an inductance, phi, equals IL. The current multiplied by the inductance value. In this case, of course, there is going to be a changing flux because there's going to be a changing current. And so the rate of change of flux is going to be L, which is a constant, times the rate of change of current. And we know that EMF is equal to minus the rate of change of flux, which of course is going to be minus L di by dt. So what you've got in this coil, in this solenoid, is a changing current which is generating a changing electric field. Indeed, a changing magnetic field. Indeed, the magnetic field is going to be going from north to south one way, and then as the current changes direction, it will go from north to south the other way. So the magnetic field is going to be pointing in that direction, then in that direction, then in that direction, then in that direction. A constantly changing magnetic field. And what happens if you have, here is the inductor, here is the current, which for the time being is flowing in this direction. Of course, it's going to change direction because the frequency will mean that it will change its polarity. But for the time being, let's just think about the current flowing in this direction through the inductance and generating a magnetic field, a changing magnetic field. What does a changing magnetic field do in the presence of a wire? Answer: it creates an induced current. Which direction does that current flow? Answer: Lenz's law tells you it flows in the opposite direction so as to oppose the change that caused it. That's what Lenz's law tells us. So although there is a current flowing in this wire, and it's a changing current, the changing current produces a changing magnetic field, and the changing magnetic field produces an induced current that flows in the other direction. And thus, the current, the main current, is impeded by the induced current. Of course, very quickly the actual current will be flowing in the opposite direction, and then the induced current will oppose that. Now, why therefore should it be that as the frequency increases, the reactance, the resistive effect of the inductor should also increase? Well, think, the higher the frequency, the more rapidly the magnetic field is changing, which means that the rate of change of flux is greater. So if you have a greater rate of change of flux, you'll have a greater EMF, and that greater EMF will produce a greater induced current. So in other words, as frequency increases, that means that the rate of change of flux increases because it's changing more frequently. So that goes up. That means that the EMF increases because EMF is equal to minus d phi by dt. And that means that I induced increases. And that means that the resistive effect increases. So as the frequency increases, the resistive effect of the inductor increases, and that's why the two go up hand in hand. Now there is something else that we can note by experiment, and that is that if we look at the voltage and the current going through the inductor, here is the voltage again, sine wave from the alternating current supply. What happens to the current on this occasion? Well, this time the current lags behind the voltage. So in the case of the capacitor, the voltage was behind the current. This time with the inductance, the voltage is ahead of the current. This is the voltage, this is the current. So the voltage starts out first, and then the current follows behind. And again, the phase angle is pi over 2, but this time it's plus pi over 2 because the voltage is ahead of the current. And you'll notice again that you cannot say that the voltage at any particular time is equal to the current at any time times R. You cannot say that. That is not true, because when the voltage is at a maximum, the current is 0. When the current is at a maximum, the voltage is 0. But you can say again that taken over the entire cycle, V RMS, root mean square, is equal to I RMS times R, which of course is the reactance XL. And now if we draw our phasor diagram, remember for resistance it went out like this, the phase angle was 0. For capacitance it went down like this, the phase angle was minus pi over 2. And you can probably guess that for an inductor, the size of the inductance is measured by the length of the line, and the angle is 90 degrees or pi over 2. So just to recap on the phasor diagrams, if you're drawing a resistance, it will be R in this direction with a phase angle of 0. If you're drawing a capacitance, then the reactance value is the length of that line and the angle is at 90 degrees. And if you're drawing an inductance, then the reactance effect is the length of that line with an angle of plus pi over 2. And so the question comes, what happens if you put a resistance, a capacitor and an inductor in the same circuit? Well, let's consider if you simply have 3 different resistances in a circuit. So here is resistor R1, R2 and R3, all in series. We know that the total resistance of that circuit will be R1 plus R2 plus R3. And that will be measured, of course, in ohms. So, is it true that if you have a resistance and an inductor and a capacitor, all in series, we know that the resistive value of the resistance is just R. We know that the resistive value, called the reactance, of the inductor will be omega L. and we know that the resistive effect, the reactance of the capacitor, will be 1 over omega c, is it true that the total resistance is equal to R plus omega L plus 1 over omega c? And the answer is no, that is wrong. And the reason that that is wrong is that you have taken no account of the fact that there is a phase angle associated with the capacitor and with the inductor. Let's, for simplicity, just consider a circuit in which we have an inductance and a resistance. We'll come to a capacitance in a moment, capacitor in a moment, but for the moment let's just keep two elements in our circuit. You would have to draw your phasor diagram, which would have the resistance here and the reactance of the, so this would be length R for the resistance, and your reactance would be in the vertical direction. Incidentally, you can show dimensionally that the reactance for the inductor and indeed the reactance for the capacitor are in units of ohms, so they have a resistance dimensionality. And the way you calculate the net, what's called impedance, of these two devices is to apply the rules of Pythagoras. Pythagoras says that the length of this diagonal line is the impedance effect of the two devices. And I think you'll see relatively straightforwardly that Z is equal to the square root of R squared plus XL squared. It's just plain Pythagoras. You can also see that the phase angle, which in this case is phi, which is neither 0 nor pi over 2, that the tangent of phi is equal to XL divided by R. So the phase angle, the angle by which the voltage and the current will be out of phase, is determined by the relative sizes of these two devices. You'll see that because it's positive, that means that the voltage will lead the current. Now, in order to ensure that we don't ever mix up the reactance and the resistance, what we do is we draw the reactance on the y-axis, which is often called the imaginary axis. For those of you who don't know, the I is the square root of -1. And since the square root of -1 doesn't exist, it's called an imaginary term. So we tend to draw an imaginary axis and a real axis, and we put the resistance on the real axis and we put the reactance on the imaginary axis. And this means that we can say in vector terms that the impedance Z is equal to R plus IXL. That way we've kept the two things entirely separate, because you can never mix real numbers and imaginary numbers. It's just a mathematical device. There's nothing imaginary about the reactance. It's just a mathematical device to keep the two entirely separate. And now we can do a little bit more maths. I think you will see that from this triangle here, R is Z cosine phi. Right, because R over Z is cosine phi, so R is equal to Z times cosine phi. Similarly, you'll also say that XL is equal to Z sine phi, because X over Z is the sine of phi, so X is Z times the sine of phi. And that means that Z is equal to R, which is the value of Z cos phi, plus I times XL, which is Z sine phi. And that means that Z is equal to the modulus of Z, that's what these terms actually are, the length of the value of the impedance, times the modulus of Z into cosine phi plus I sine phi, because I've taken the Z's out both sides. So the total value of the impedance is equal to the modulus of the impedance, the value of its length, times cosine phi plus I sine phi. But mathematically, this term is e to the I phi, so you get that the total value of the impedance is equal to the modulus of the impedance, that is the, as it were, the absolute value of the impedance, times e to the I phi, because this term is mathematically equivalent to that term. So what are we going to do if we have all three components in a circuit? A resistance, an inductance, and a capacitance, all in the same circuit. Well, we plot our phasor diagram, which is going to have three elements on it. Firstly, it's going to have an inductance, XL, then it's going to have a capacitance, XC, and then it's going to have a resistance, R. And how are we going to construct our diagram in order to do our Pythagoras? Well, it's quite simple. The net effect of the two reactances, which are both in the same plane, they're both on the I scale, this is the imaginary scale, this is the real scale, you can simply subtract one from the other, and the net effect of this will be this distance here, which is simply XL minus XC. It will depend which is the larger. Obviously, if XL is greater than XC, then there will be a small surplus in this direction. If XC is greater than XL, there will be a small net effect in this direction. But it's the net effect of XL minus XC, which is what you construct, and then the total value of Z will equal the square root of R squared plus the net reactance squared, which is simply XL minus XC all squared. And the angle, the phase angle, which here is phi, will be given such that tan phi is equal to XL minus XC divided by R, because this value here is XL minus XC and this line here is R. And the angle phi will be the extent to which the voltage lags or leads the current. In this case, it's a slight positive angle, and so consequently, if we draw the voltage, then the voltage will lead the current by this angle, whatever that turns out to be. So the current will be a little bit behind the voltage by the angle that we have calculated. Now, although resistances and reactances have the same dimensionality, they can all be measured in ohms, there is a very important difference between the two. So let's now take our circuit. It's an alternating current circuit in which we have a resistance, an inductor, and a capacitor. Now, the important thing about the difference is this, that a resistance will dissipate power as current flows through it. And the power loss in a resistor is given by the voltage times the current. Or you can sometimes, using Ohm's law, you can say that that equals I squared R. We've dealt with this in previous videos on electricity. So there is a power loss in a resistance. But there is no power loss in a perfect inductor or a perfect capacitor. I say perfect because, of course, in practice, there will be some element of resistance in both. But in theory, at any rate, and in terms of exams, you usually think in terms of the theory, there is no resistance associated with these, only a reactance. Consequently, what happens with these two devices, there is no power loss. In a reactance, what you get is energy storage and dissipation. The capacitor charges up, and as it charges up, it collects and stores energy, and then as it discharges, it releases that energy. The inductance is building up a changing magnetic field, which is a build-up of energy and then a dissipation of that energy. So there's no power loss in these two devices, only in the resistance. If we measure the voltage drop across these devices, firstly put our voltmeter across the resistance and get a voltage reading of VR, which is the potential drop across the resistance, and then measure the total voltage drop across the two reactances, the inductor and the capacitor, and that will give us the voltage drop Vx. And let's say the total voltage of the AC supply is V. You might be tempted to think that the total voltage is equal to the voltage dropped across the resistor plus the voltage dropped across the reactance. And again, you would be wrong, because you would have forgotten the fact that we've got phasor diagrams to have to deal with. So once again, we have to draw our phasor diagram. We will have Vx along the imaginary axis and VR along the real axis. And so again, you have to do your Pythagoras, and you will find that the net voltage, which is the root mean square voltage, is given by the square root of this term squared, VR squared, plus this term squared, Vx squared. So you don't just add them together, you have to do the Pythagoras. Now, what is the power loss in this circuit? Well, we've already said the only place you lose power, at least in theory, is in the resistance. So consequently, the power loss is going to be VR times the current flowing through the circuit. So the power loss, and we're going to do the average power loss through the resistance R, because that's the only place you lose power, is going to be the root mean square of the current times the voltage across R. But if you look at this diagram here, you'll see that VR over VRMS is equal to the cosine of the angle phi. VR over RMS is the cosine of the angle phi. And that means that VR is equal to VRMS times the cosine of the angle phi. So we can substitute this VR, I should have used the same R, this R, VR for here, and that means that we get that the power loss across the resistance is equal to IRMS, which is this term here, times VR, which is VRMS times the cosine of the angle phi. So if you know the root mean square of the current and the root mean square of the voltage, multiply that by the cosine of the phase angle, and that gives you the power loss in the resistance. And how do you find phi? Well, if you know the voltage drop across the reactances and the voltage drop across the resistor, then you will readily see that Vx over VR is the tangent of phi. Vx divided by VR is equal to the tangent of the angle phi. So if you know Vx and VR, divide one by the other, and that's the tangent of the phase angle. Now finally, before I do some worked examples, because people have been asking me to do some examples, but before I do that, I just want to look at what's called resonance. And you get resonance in LRC circuits. That's where all three of the components apply. And the usefulness of this, just to tell you where we're going, is this is precisely how you tune in your radio and your television. So what you've got is what's called an LRC circuit. So we're going to have an alternating current supply going through a resistor, an inductor, and a capacitor. And usually we make that a variable capacitor. And the way you make a capacitor variable is you've got two plates. I'm using my hands to represent the two plates of the capacitor. Now I turn it edge on, and as you turn the dial on your radio, what you're effectively doing is turning one plate against the other. And therefore the degree of overlap, the amount of area that is common to both, reduces or changes. And that of course changes the capacitance. So the way you change a capacitor is you swivel one of the plates so that the amount of area that is common to both reduces or increases as you turn it, and that therefore becomes a variable capacitor. So let's just remind ourselves that the total impedance of this circuit is going to be the square root of the resistance squared plus the capacitance squared. And in that case, we've got that the total impedance is the square root of R squared plus XL minus XC, all squared. And that is the square root of R squared plus, well, the capacitance of XL, as we've said, is omega L, minus the capacitance XC is 1 over omega C, all squared. Now think about this term here. This term squared will always be positive because any term squared will be positive. It matters not whether omega L is bigger than or smaller than 1 over omega C. It doesn't matter whether this term is positive or negative. When you square it, it will come out positive. So Z will always be the square root of R squared plus a positive term. That means that Z, the impedance, will be at its minimum when this term is 0. And that means if the impedance is at its minimum, the current will be at its maximum because V equals IR, V equals IZ. When Z is small, I will be large. So when this term is 0, you get the minimum impedance, maximum current. So what does it mean for omega L to equal 1 over omega C? Because if that's the case, then this term will be 0. Well, multiply this out and you get that omega squared LC equals 1, which means that omega is equal to 1 over the square root of LC, which means since omega is 2 pi f, it means that the resonant frequency, the frequency at which this term equals 0 and therefore the impedance is minimized and therefore the current is maximized, that frequency is going to be 1 over the square root of 1 over 2 pi times the square root of LC. And if you draw a picture showing the current against the varying frequency, what you will find is that it will suddenly shoot up when you get to the resonant frequency, because that's the point at which the impedance is minimized, so the current is maximized. And this is typically what you're doing. Your radio is picking up all sorts of frequencies, but only at the frequency that is, as it were, maximized, where the current is maximized because you have achieved a minimum Z by making this term equal to 0. It is the current for that frequency which is maximized, and that's why you can hear that station on your radio. All the other frequencies are down at minimal levels, so you don't get to hear them. But if you change the capacitor, then you will change the point at which, the frequency at which this term becomes 0. And so if you change the capacitor, the resonant frequency changes to here, a second resonant frequency. So this may be one of your favourite channels, and that may be your second favourite channel. And by varying the capacitor, you can change the frequency at which the signal will be maximised. That's how, essentially, radio and television tuners work. Now, I said I'd do a couple of examples, which I dread doing because I'm terrified I shall make a mistake. So if I do, you'll tell me. But let's take the situation where we have an alternating current and a circuit which is simply a resistance and a capacitance. And the values are that the resistance is 100 ohms, the capacitor is 10 microfarads, the VRMS is 250 volts, which means it's kind of broadly the United Kingdom power supply that comes from the wall. The frequency in the United Kingdom is 50 hertz. And what we want to know is what is the root mean square current that is flowing in the circuit. Well, we remind ourselves that VRMS is equal to IRMS times Z. That is essentially the Ohm's law for impedance. We also know that the impedance has a value of the square root of R squared plus the reactance squared. Reactance, of course, is the capacitor in this case. and we know that xc is 1 over 2 pi f times c. We know f, that's 50 hertz. We know c, that's 10 times 10 to the minus 6 farads. Remember, you have to convert the microfarads into 10 to the minus 6. If you put that all in to a calculator, you should get that this is the equivalent of 318 ohms. Remember, reactance has the same dimensions as resistance, ohms. And then Z, using this formula here, will equal the square root of R squared. R, remember, was 100 ohms, so R squared is 10,000, plus 318 squared, which will be 101,321 approximately. And if you take the square root of that, you should get 333 ohms. So the net impedance of the two devices is 333 ohms, which means that the root mean square of the current, which is what we want, is V RMS divided by Z. This is, of course, simply Ohm's law. I equals V over Z. And that is equal to 250, which is the root mean square voltage, divided by 333, which is the net impedance. And that comes to approximately 0.75 amps, which is what we were asked for. But let's just go a little bit further and think about the voltage travelling through the across the resistance. Well, the voltage across the resistance will simply be the root mean square current times the value of the resistance. Well, that's 0.75 is the current, we just calculated that, times 100 ohms, because that's the value of the resistance, and that's 75 volts. So if you measure the voltage across the resistance, that's what you'd measure. The voltage across the capacitor is going to be I RMS times the reactance of the capacitor, which is again 0.75, because that's what we calculated, times 318, because that, remember, was the value of the reactance of the capacitor, and that comes to 238.5 volts. And you might be tempted to add the two together and get 313.5 volts and say that can't be right because the voltage is 250 volts. And of course you've made the mistake of adding together these two voltages. You can't do that, remember, because they're on different axes. One's on the imaginary axis, one's on the real axis. So you have to plot the phasor diagram, and that means that V is going to be equal to the square root of VR squared plus Vx squared, which is the square root of VR squared, 75 squared, plus Vc squared, which is 238.5, all squared. And if you take the square root of that, you should get 250 volts. And now let's look at an LRC circuit. We've got a resistance, an inductance, and a capacitor, all in the same circuit. I can tell you that the resistance is 25 ohms, the capacitance is 50 microfarads, the inductance is 200 millihenries, the RMS voltage again is 250 volts, and the frequency is 50 hertz, what you'd get from the UK mains broadly. And what we want to know firstly is the total impedance of the circuit. Secondly, we want to know what the IRMS, the root mean square current, is. And thirdly, we want to know what is the phase angle, what is the either the lagging or leading of the voltage by the current. Well, we remind ourselves that the impedance is always going to be the square root of R squared plus the net effect of the reactance squared, which in this case will be R squared plus XL minus XC squared. And that's going to be the square root of R squared plus 2 pi FL, because omega L is the reactance of the inductor, minus 1 over 2 pi FC, i.e. 1 over omega C, all squared. And if you substitute in here, R, remember, was 25, so the 25 squared is 625, plus, if you work this out, you get 62. If you work this out, you get 63, all squared. So 62 minus 63, you're almost at resonance. This is almost 0. And that will come out to the square root of 626, which is broadly 25 ohms. So the net impedance of the entire circuit is 25 ohms. We know that VRMS is equal to IRMS times Z, and of course we know that VRMS is 250 volts. We've just calculated Z, so obviously IRMS is going to be VRMS 250 divided by Z, which is 25. That means that IRMS is equal to 10 amps, which is a high current. And the tangent of the angle, the phase angle, is given, as you know, by X over R, and the net effect of X is 62 minus 63, which is minus 1, over R. Well, the resistance was 25 ohms, and so you've got an angle which is a negative angle, which means that the current will lead the voltage, or the voltage will lag behind the current. It has a capacitive effect, and phi is minus 2.3 degrees. So it's a very small angle, so the current will barely lead the voltage at all, but only just. The current will be just ahead of the voltage in this particular circuit. And just to show you what I mean by resonance, remember in that circuit we had a total current of 10 amps. Suppose that the frequency, instead of being 50 hertz, which is what I said it was, suppose it were 100 hertz. Then you would have that Z is equal to the square root of R squared plus 2 pi FL minus 1 over 2 pi FC all squared. But this time you would use F is 100 instead of F is 50. And so you would get that the total impedance would be R squared, which is 625, plus this term with F as 100 will now come out at 125, and this term will come out at 31. So now you get 125 minus 31 squared, and that will give you a total impedance, if you calculate it, of 97 ohms. And now we can still say that VRMS is equal to IRMS times Z, the total value of the impedance. And that means that IRMS is V, which is of course still 250, divided by Z, which is 97. So IRMS is going to be equal to 250 divided by 97, which is about 2.5 amps. So when the frequency was 50 hertz, as in the previous page, the current was 10 amps. When the frequency goes to 100 hertz, the current falls to 2.5 amps. It's moved quite a long way from resonance. 2.5 amps, of course, is still a quarter of 10 amps. So if you were tuning, you'd get quite a lot of interference. The skill with LRC circuits is to adjust the values of L, R and C such that at resonance you get a very high peak of current, but everywhere else you get hardly any current at all.